Okay, we're going to prove that the integers are not isomorphic to the rational numbers under addition. And this might first come to be slightly counterintuitive. And that's because, well, you know from earlier math courses that the cardinality of the integers is equal to the cardinality of the rationals. In other words, there is a bijection between the integers and the rationals. Some other tests that you can do to check if something isn't isomorphism is you can check if both groups are abelian. So we know that the integers are abelian, like a plus b is equal to b plus a, and you can do the same for the rational numbers. It's pretty straightforward, so that's fine. And another slightly more technical test you can do to check if two groups are not isomorphic is you have to check if one of them has an element which has a different order to an element in the other group. So I'll be a bit more precise. So if you have, for every element x in z, and if we had some isomorphism between z and q, then for every element in the domain, we have the following property, okay? The following property is that the order of x is equal to the order of the image of x. Okay, so for example, we have the element number in the integers, we have the number 0, which has order 1, because you just have 0 is equal to 0, and then every other element in the integers has order infinity. Because let's take the number 2, we go 2 plus 2 plus you're never going to get 0, so that's got order infinity. And you have negative numbers as well, they also have order infinity, and you can have the same argument for the rational numbers. So all the elements have the same order. Okay. Well, okay, we're kind of stuck. The basic tests have all failed to prove that they're not, these integers and rational numbers are not isomorphic. Okay, but not to worry, there is another test. And in fact, it comes from, or the motivation for this test comes from a key observation. Okay, and this key observation will underpin the reason why the integers and the rationals are not isomorphic. Maybe you come away from this video with the actual proof technique, but it's important to also understand why the integers and the rationals are fundamentally different beasts. Okay? And the reason why is because if I draw a number line for the integers, like this, okay, and I'll put 0 here, we have 1, and we have 2, -1, -2, or whatever. Alright, for the integers, it's pretty straightforward to see that every element in the integers can be reached by starting at 1, and then just adding more ones or subtracting ones. So by adding more ones, we have 1, we go to 2, we plus another one, we get to 3, and so on, we get to 4, blah, blah, blah. You can get to any integer. And you can also get to negative integers as well by subtracting. You have 1 minus 1, minus 1 again, minus 1 again. Oh, forgot my little minus sign. And you can continue on forever. Okay. For the rational numbers, this is just not the case. If we started with the number 1 in the rational numbers, and we kept adding 1, we'd get to 2, and if we started subtracting, we'd get to 0, and then get back to -1, and so on. But you know what would be missing? We wouldn't hit or touch the rational number 1/2, okay? Alright, what if we suppose that 1/2 was our generator of our rational numbers, the thing that we can start at and add a bunch of times to reach everything else? We start at half, we get to 1, we get to 1 plus 1/2, and so on. But now we're missing this value. And if we started here, then we would obviously miss this, and then we'd miss this, and you can keep infinitely dividing, and you're never going to find a value which generates the entire rational numbers. So that is the fundamental difference between the integers and the rationals. It's that the rationals don't have a single generator element. Okay. So we're going to prove a key fact or lemma, and this is the following statement. All right. If phi from G to H is a surjective map, or a surjective homomorphism, and G is generated by a single element, then H is generated by an element. Ooh. Remember, generated just means if you start at that value and you keep adding it, you can reach everything else. Okay. So the way we can prove it is I'm going to start with a small little visual, and hopefully this provides some intuition with the proof. So on the left hand side, this is going to be our group G, and on the right hand side, this is our group H, and we have a surjective homomorphism phi. And so first of all, what does it mean for phi to be surjective? It means that for any element in H, we have at least one element in G which gets mapped to H. So if this was X, there always has, you can cover all of H. Okay, that's the intuition behind phi. In some sense, you can take a point and there always exists something in G which gets mapped to it. All right. Okay, what's another fact about this sort of setup is that G is generated by an element. So there is some special element in G, let's call it S, such that any other element in G, I'm going to call this one T for some reason, we can re-express T as being S to the power of K, where to the power of just means like repeating the same binary operation again and again and again, K times. So you have S to the power of 1 here, or you might have S to the power of 2, S to the power of 3, da 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 da. You have S to the power of K minus 1, and then if you multiply this value by S, finally you'll reach T. And this is true for any element in the set G. Okay. So, here we'll go. We'll start the proof, alright? Since, okay, well first of all, we'll pick some completely arbitrary element in H. Here. This one here. And now, since our phi is surjective, that means there exists an element G in our big group G, where H is equal to phi of G. Okay. Now, notice because G is generated by S, we can rewrite our G here as G is equal to S to the power of K, like that. Okay, and if we plug this definition back into our original phi, we get phi S to the power of K. Okay, so this thing is S to the power of K, and this thing is phi of G, which is equal to phi of S to the power of K. Alright. Now, here's an interesting fact that you can prove by induction, and it's not too tricky, so I recommend you try it. Like, you should be able to just quickly do it. Phi of S to the power of K is equal to phi of S to the power of K. Alright? And you use the fact that phi is a homomorphism here. Okay. Now, note phi S, this is just some value in our group H. So we've fixed S to begin with because G was generated by it. So, you know, phi S sits somewhere like here or something. I don't know. And then if we raised this to the power K, we're going to eventually reach our arbitrarily chosen H. Okay, so it didn't matter which h we picked. We started off at phi s, and we can add phi s together so many times, and we reach h. Okay. In other words, h is equal to phi g, which is equal to phi s to the k, which is equal to phi s to the k. Thus, phi s is a generator of h. Okay, awesome. All right, I've run out of room here. Okay, so we wrote h is equal to phi g equal to phi sk, which is equal to phi s to the k, and therefore we know that h was generated by this element. In other words, phi of s is a generator of h. Okay, so we've proven the lemma. If you have a surjective group homomorphism phi from G to H, and our domain group G is generated by one element, then H, our codomain, is also generated by one element. Alright, so here's how we're going to prove the whole integers and rationals are different. So by way of contradiction, let's assume there is an isomorphism phi from the integers to the rationals. Look at this, okay? So we know the integers are generated by the number 1. Okay, so you can get to any other integer by just adding 1 a bunch of times. Right, and so let me draw the little diagram. We have our integers, and this can be our rational numbers. Rationals, cool. So we know that these are generated by the number 1, then by the lemma before, because an isomorphism is a bijection, and a bijection is an injection and a surjection. Therefore, we have a surjection from a group which is generated by one element to another group, which therefore means, by the previous lemma we just proved, the rational numbers should be generated by a single element. Okay, and that single element is going to be whatever phi of 1 is. Okay, so this is some fixed value that we know about, and we can rewrite this as m divided by n. Okay. So now what we're going to do is we're going to pick some completely arbitrary value in the rational numbers obeying a particular property. So we're going to call it 1 over q, and we're going to say that q does not divide n. And you could pick this, like if phi 1 happened to be like 1/3, then you could pick like your 1 over q to be equal to like 1 over 2 or something. Like that's fine, 1/2. And you can always do that. I'll write that here. Q does not divide n. Okay, important fact. We'll use this later. This will be used in the actual contradiction point. All right. So now, because we have an element in the rationals, 1 over q, that means by the fact that phi is a bijection, but because it's a surjection, we know that there must exist some integer k in the integers, which when you do phi k is equal to 1 over q. Okay, so this has to be the case. All right. Now, what we're going to do is we're going to rewrite phi k as k times by phi of 1, right? And we're using multiplicative notation here. We're using additive notation here. Alright. So we've expressed 1 over q, which is phi k, as k times by phi of 1. Right, and we'll substitute this definition in. So here we have k times by m on n is equal to 1 on q. Right? And if we multiply both sides by q and both sides by n, what do we get? We're going to get k times by m times by q is equal to n. Alright, and here's where you'll see the actual contradiction. We can group this. We have km, q is n. So q has divided n here, but by our choice, we have chosen q so that it doesn't. And therefore we have a contradiction. So therefore, no isomorphism exists. Phi from the integers to the rationals exists. So the key fact that makes the integers and the rationals under addition different is that the integers are generated by a single element, 1, whereas the rationals do not have this property. Okay, that's like the intuitive takeaway for why these are different. Anyway, thanks for watching.